For this problem, we were given 4 different values, all correlating to a covertice point and a focus point on a hyperbola graph that we'll find later. So first I found that my covertice would be 6, 7, which is this point right here on a Cartesian graph, and the focus is 20, -8. We just made this negative for fun, which would be right here, this point right here. And then, so that because I know that the center shares the y value because it lies along the same imaginary like y line right here, and the x value with the focus, that same principle, but an imaginary x, I know that the x value of the center should be the same as this one, and the y value of the center should be the same as this one, which gives me my center of 20 and 7. And that becomes really important for this equation later on because I need to find this hyperbola equation to later find my parametric equations of this hyperbola. So I can now fill in where the center is on here, y minus 7 and x minus 20. And then now I can start working on finding where the vertex is, like how far this distance, the center from this dot right here, the one that's on the hyperbola curve. I need to find that distance to write in for y, which you'll see coming up. So to do that, I know that the distance from my center to my focus is 15, and that should be technically the longest distance in this kind of setup. So I can draw a triangle. So imagine this to here, and then like kind of here. So this should equal 15. That's the longest. So that'd be our metaphoric hypotenuse because that value should technically be the longest out of the 3 we're comparing or using in the triangle. So my next value would be the distance from here to here, from the covertice to the center, which is 14. So that's my longer side of the triangle. And then the one I'm trying to find is B, which is the distance from here to here. So to find that, I can use c squared equals a squared plus b squared. And because I already know c squared and a squared, I can just do 225 minus 14 squared, and that equals 29, which equals b squared right here. And I know that now that my b, this distance from here to here, is root 29, which I can now fill in for my hyperbola, and that goes underneath the y minus 7 because that's like the y distance from here to here. And now I have 14, which is distance from here to here. And that allows me to establish my equation for the hyperbola, which then I can like use solve backwards to find this. So for each of these, I'm going to isolate each one. We are going to use the identity secant squared minus tangent squared equals 1. This being secant squared in that case, and this being tangent squared. So by knowing that, you can see right here that I'll end up with a tangent t, which is part of the parametric, and secant with a t again. So I'll set this equal to secant squared, this y minus 7 over root 29 all squared. And then by solving that and isolating for y, I get root 29 secant t plus 7. And that comes from that. And then because the same principle follows for the tangent, I set all this whole thing, x minus 20 over 14, all of that squared, equal to tangent squared. And then by isolating the x again and solving for x, I get 14 tan t plus 20.